Welcome to 3.4, Velocity and Other Rates of Change. Okay, it's very natural for us to think that when we hear rate of change, we think in terms of time. However, it's important for us to understand that there are many variables that depend on other things besides time. A lot of our formulas don't have time in them. Our geometry formulas, for example. Here I have a drawing of a sphere, and the volume of the sphere is written. The volume is a function of the radius. It has nothing to do with time. We should still be able to take the derivative. So what would that mean to find the derivative? Well, our variable is not x or time or something like that. It's r. So we're going to go ahead and differentiate with respect to r. Okay, so what is d/dr of 4/3 pi r cubed? So we'll just use our power rule. Bring the 3 out to the front and multiply it with the 4/3, and then we'll take 1 power off the r, and we'll be left with v prime r equals what? 4 pi r squared. Okay, so let's just rewind back here a little bit. If you look at the sphere and suggest maybe that it's measured in inches for its radius, you can see the cubic inches here for the volume. Now what do we have here for our derivative? We have square inches. Square inches. So this must be some kind of an area. Well, it turns out, and if you look this up, you'll find that this is the actual surface area of the sphere. Now that might surprise you at first, in that why would taking the derivative of the volume provide us with the surface area? Well, it turns out it makes good sense. Let's look at why. Let's say that you wanted to increase the area, or excuse me, increase the volume of a sphere, but you wanted to do so in a very gradual way. Well, to do that you would need to add a surface. So you would basically sort of paint over the outside of the sphere, and in so doing you've actually increased the volume. And how's that? It's because the paint has thickness, right? So you've just added on, you've made the volume go from 4/3 pi r cubed to something like 4/3 pi r plus h cubed. So how is it that volume grows? By surface area. So the rate of change for volume is surface area, the instantaneous rate of change. Okay, now the word instantaneous here makes it sound like we're doing something over time, but we need to remember that that word actually gets used probably too much in math, that it has really nothing to do with time. It's just by an increment, a slight change in radius, we produce more area and more volume, and the actual rate is according to area. Okay, now it's your turn. Here's a cube. Now we're going to actually go ahead and write out the function for the volume. We want to probably try and make this as much like the sphere as we can so that this all works out for us. So what I'd like to do is define our volume a little bit differently. I'd like you to base your volume function on this length, which we'll call x. So this is inside the cube. From the center of the cube to the center of one of the faces of the cube. We'll call that x. Why don't you set up your volume there? Why don't you pause the video and try it? And once you're done writing out the volume function, find the derivative with respect to x and verify that it does actually equal the surface area of the cube. And we'll go over that in class next time. Okay, now if we bring this down to the second dimension and just draw a circle, so this is not a cube, we can talk about how area changes. Okay, so the area of a circle, of course, is written in terms of its radius as well. So it's simply pi r squared. But what does the derivative look like? I went ahead and included the extra of r there. That's optional. Well, you'd bring the 2 down, and you'd reduce the power from 2 to 1. Now this should look familiar to you. This is simply what? Circumference. So the rate of change, the instantaneous rate of change for a circle's area is its circumference. Okay, and now it's your turn. Let's write down the area of this square based upon x. And again, we'll measure x from the center out. Then find the derivative of the resulting function and verify that it equals the analogous, that it's analogous to finding the circumference of the circle. And then maybe you can write a sentence about this scenario, and we can discuss it. Okay, here's a word you'll see quite often, displacement. Not to be confused with distance. So some of you know what this word means already. The word displacement just means literally change in position. So if something moves 1 inch, its displacement is 1 inch. It's not to be confused with distance. You could be moving from one place to another, let's say from here 1 inch this way, and then 1 inch this way, and then 1 inch this way, and then 1 inch this way. And although your distance traveled is 4, your displacement is actually 0 because there was no change in position. You started where you were. You started here at the beginning and you ended up where you started. And of course, if you travel in a straight line and you only go one direction, then your displacement does add up. So you go an inch, and you go another inch, and you go another inch, and you go another inch. You've traveled 4 inches, that's your distance. It's also your displacement. So it's a change in position of 4, not just a distance traveled of 4. Okay, now let's say that these 2 journeys required basically 1 second per portion of this journey. So let's say you did 1 second to do each of these 4 inches. Your average velocity would basically be your displacement over the elapsed time. Of travel. Okay, so this would be 0. So despite the fact that we traveled 4, the velocity average is actually 0 for this. And for this drawing, the velocity average is 4 inches. I should put units on these. So 4 inches in 4 seconds. And the rate is 1 inch per second. So when we use the word velocity here, you can see it can't possibly mean speed on its own, because in both of these cases, it took us 4 seconds to travel 4 inches. And so you'd think the speed is 1 inch per second, and it is. But the velocity is not 1 inch per second. It is 0 inches per second for the first one, and 1 inch per second for the second one. Again, the difference is we're measuring velocity to mean displacement over elapsed time, not distance traveled over elapsed time. So the official formula is displacement over elapsed time for velocity average. So that would be f of t plus whatever time has elapsed minus f of t all over the elapsed time. So this is your displacement here. This is your position difference. This is the position when you started the motion, and this is the position when you ended the motion. The change in position. Now, of course, the instantaneous velocity, and now we are talking about rates of change involving time, right? Would just be putting a limit as delta t goes to 0 on this. So not allowing for a time delay. And we won't need to write instantaneous, we'll just write v. And this will be the limit as delta t approaches 0 of f of t plus delta t minus f of t all over delta t. Okay, now what I'm about to say is very, very important. Please understand that we're dealing with velocities and not just speeds, as I said a few minutes ago. It's very, very important that you understand that a negative velocity would mean that you're traveling in a way that decreases your displacement. So the example they gave was a person maybe who's traveling from school to home, from home to work or something. On the way there, they would be reading their speedometer to say, let's just say 40 miles an hour. But on the way back, they might read it to mean read it to say 40 miles per hour. But it would not include the negative that involves the opposite direction. So as we know, speedometers measure speed, but the velocity going to somewhere and velocity coming back from somewhere differ by a minus sign. In other words, velocity does include direction. Okay, this problem is from the book. This is our first chance to read a velocity graph. Please take a moment, pause the video, and copy down the problem. Okay, you got it? Alright, let's look closely at the units involved. According to the instructions, we're going from -4 to 36 on our window settings. So this must be 0, 4, 8, 12, 16, 20, 24, 28, 32, and 36 seconds. This is going from -7.5 up to 7.5. So it seems that these are just labeled in 1, 2, 3, 4, going up. Okay, so if you don't mind, I'm going to erase all that. You can go back and put that in if you like. Okay, remember again that the y-axis is velocity, not meters, but some sort of speed. Okay, now the book asks us to analyze the actual motion. We can do that sort of thing, but I mainly wanted to point out this question here from their example. At what time was her speed a maximum? Okay, so the velocity graph shows us points like this one, where the speed is 4. So this is at the 4th second, and the speed is 4. And there are other points in here, and there's this one where the speed is 4, or the time is 8th second, and the speed is still 4, see? Now, are there any other times on this graph where the speed is higher? Well, you might be looking over here and thinking, okay, over here at the 36th second, the speed is 4, so that's a good candidate for the highest speed. But remember, we're talking about speed. Speed is absolute value of velocity. So actually what we're really looking for is this point right here. This point is at 20, -7. So the velocity is -7, but the speed, being the absolute value of velocity, is 7 units per second, and that is faster than 4. So it is not up here that we should be getting our fastest speeds from, our highest speeds. Our highest speed is actually right here, the point furthest from the x-axis. Okay, so far we have position, which the book uses S of t for, and velocity, which is the derivative of the position with respect to time, and acceleration. Acceleration is the rate of change of velocity. So it's like the speed of the speed, and you'll find that of course then is the derivative of velocity with respect to time. So we call this the second derivative of position. It's the derivative of the derivative. It's the rate at which the speeds are changing. The units for these sorts of things are, as you know, like meters per second squared, or as some people say, meters per second per second. But this could be any linear unit. This could be inches, hours. So it could be inches per hour squared, for example. Okay, this is a very famous type of problem called motion on a line. We're going to be studying the x-coordinate of a particle that's moving back and forth on the line y equals 2. We're going to keep track of its x-coordinate using this function. Probably the most informative thing to look at would be the graph. Take a moment and enter this as y1 into your calculator. You'll be using x for your t. The window that I'm using here, by the way, is from -1 to 5 on the x-axis using x scale of 1, and from -50 to +50 on the y-axis using a y scale of 10. You can also set up the table. I'm using table start of 0 and a delta TBL of 0.5. Now this is your position graph. So it might be wise to try and figure out where these points are that are maxima and minima. And the reason for that is our velocity is going to be determined by the slopes of the tangent lines along this curve. So anytime these lines are pointing in the direction of positive slope, we can assume that the object is moving forward. And if negatively sloped, the object is moving backwards. And forwards. Spots where there's a horizontal tangent, say here and here, can be found using the math calc features on your calculator. So you can go to the calc menu and you can go down and select maximum and position your cursor so it's to the left of where you think the maximum is, and press enter. It will ask you then for a right bound. You can go to the right of it, press enter again, and then take a guess as to where you think it is, pressing enter a third time. We're getting 1.652. Now let's go find the other point, which seems to be a minimum. It looks like 3.680. Remember, we're using 3 decimals. Okay, so let's go back to our description. We can say that it was moving forwards first we might want to say where it started. We can just say it started at, and this is for t equals 0. If you plug in 0, you get x equals negative 45. And the y was 2 because we're actually on the y equals 2 line. So it starts at negative 45, comma 2. It moves forward from time 0 all the way up to 1.652 seconds, I believe it was. Let's go check that. 1.653, excuse me. Does it move forward at other times? Well, let's go back and look at our tangent lines again. Yes, any time after 3.680. We could just write t is greater than 3.680 there as well. Okay, when is this moving backwards? Well, let's look at our picture. Anytime between 1.653 and t equals 3.680. So moving backward. .680. Now going back to your graph, if you return back to your maximum point, so I went ahead and redid the calc for the maximum. I did my left bound, right bound, and guess, and here I am sitting on the point 1.653. This value here is x of 1.653. In other words, this is the x position for that point. It's 6.298 or 6.299. Okay, and we can also go back and look at the position of the other point. And here I did a search again for the minimum. We had recorded 3.628 prior, but we had not looked at this value, negative 10.373. This is our x-coordinate. I'll try and be accurate with these decimals. Okay, and in all cases y is 2. Okay, so we have the coordinates of the point on the xy axis. Now remember, what you see here is an x of t versus t graph. So this is seconds, and this is x coordinate. So we're not looking at an xy path here. We're going to actually draw that right now. Okay, so we started with the point at about negative 45 at time 0. At time approximately 1.653 seconds, the object was over here at 6.299, comma 2. So the path was this direction. Okay, we know that at this time the object turned around and headed back. We know that because this is where we had a tangent line at time. Let's go back and look. 1.653. That's when things turned around. Okay, now it's headed backwards, and it goes to negative 10.373. Comma 2. And this happened at time t equals, I think it was 3.680 seconds. And after time 3.680, the graph was increasing indefinitely, going upwards as time went on. The x value was approaching infinity as time went on. So that just corresponds to this turning back around and going this way forever. So it had a moment where it was backtracking, but then it just kept on going to the right, and this will never stop. So let's go back to our slide and see how we can maybe make our answer a little more specific. Okay, so in sentence form we could say the particle moved forward we could say from negative 45, comma 2, to 6.299, comma 2 in the first one point 653 seconds. Sorry, missing handwriting there. It then reversed directions and went back to the point negative 10.373, comma 2 at t equals 3.680 seconds. It turned around once more and moved to the right indefinitely.